Good morning, everyone. My name is Kaiyu, a PhD student from Texas A&M. Today, I'm going to share one of my recent work, which is about integrated scheduling and offset-free MPC of hydraulic fracturing operations. This time, I will explain the work by following this outline. So the first section should be the introduction and motivation of this project. As we know, the development of natural gas has been significantly accelerated in recent years. As reported by EIA, the largest contributor to the growth of natural gas is actually the production from shale gas and tight oil plays, which may account for nearly 92% in 2050. In this regard, shale gas is expected to be an indispensable resource to satisfy global energy demand. However, the shale gas production system is generally complex and multi-stage. As shown in this figure, a variety of decisions must be made for the upstream, midstream, and downstream operations, such as the acquisition of fresh water, the management of the generated wastewater and greenhouse gas emission, and most importantly, the well pad development as highlighted here. As for the well pad development, they are generally four stages defined. The approximate time period and the involved operation for each of them are also presented. In particular, we'd like to emphasize the hydraulic fracturing operation, which is most essential technique for shale gas extraction. Specifically, we need to inject the fracturing fluid into the wellbore for fracture propagation, following this pumping profile. At the end, a propped fracture volume can be created as shown here, which connects the rock holding shale gas and formation water with the wellbore and facilitates the flow of them. So the amounts of fresh water requirement, flowback and produced water production and the shale gas production should be determined by the hydraulic fracturing operation, which can decisively affect the design of the entire shale gas production system. So in today's shale gas industry, one common challenge is to manage those various operations in a unified and optimal manner. So a considerable number of optimization studies have been carried out to decide the optimal design and operation of shale gas system. Among them, one important decision should be where, when, and how many wells should be fractured, which can be indicated by the draining strategy and draining and fracturing schedule. Here's an illustrative example. However, one problem is that few of the studies consider hydraulic fracturing as a dynamic process. In other words, since the pumping profile determines the freshwater requirement and the resulting fracture geometry affects the shale gas production, both of them should be considered as decision variables and determined simultaneously with the schedule for better overall performance, which requires the seamless integration of the scheduling and process control. For the integrated scheduling control, an ideal complete integration framework had been explained in this review paper. As the diagram shows, the entire schedule and set points determined by the scheduling model should be provided to the control system, which relays on this information to compute online inputs. Then the real state information from the process should be sent back to the scheduling model, which uses this information to perform rescheduling. Following this structure, many approaches have been developed these years. Among them, one intuitive and systematic method in the optimization field is the dynamic optimization-based scheduling. And its basic idea is to extend the higher level scheduling model by replacing the fixed operation recipes with detailed dynamic process models. However, such an open loop optimization disregards the possible process disturbances which could disrupt the system. Also, there are few discussions regarding the batch processing, mainly due to the related higher computational complexity. In this sense, this project is mainly targeted to handle these issues. So the next will be our proposed framework and its application. Here is a diagram of the proposal framework, which has a two-level feedback loop structure. As shown, a reduced route model is developed and integrated with the schedule model in the outer loop. Then we take the optimal output reference trajectory and use an online control system to track it as an inner loop. Then the optimal inputs and outputs can be obtained from the control system, which will be sent back to the outer loop for online re-optimization. This framework is actually an extension from this study. And the major difference is the addition of the offset-free MPC scheme, because previously they did not consider that the negative impact on the reference tracking performance caused by the planned model mismatch and unknown disturbances could be alleviated or even completely removed through the careful controller design. So this modified framework has the following advantages. First, the tracking performance can be enhanced, with which the re-optimization procedure could even be avoided in many cases to facilitate online implementation and assure rescheduling stability. Second, the reduced order model that is thus not required to be extremely accurate, and thus the computational burden of resolving the integrated problem online could be alleviated. When applying the proposed framework to hydraulic fracturing, the diagram could be extended as presented here. The details will be explained later. So the online implementation of this framework is illustrated by this example. By solving the integrated model, the optimal schedule and output reference are obtained. Then for the first wall starts to be fractured, when the first wall starts to be fractured based on the offline schedule, the online control system will be initiated to track the reference. Once this wall path is completed, the real freshwater consumption and the shale gas production will be sent back. Then the integrated problem will be resolved online for the remaining wall paths and in a reduced schedule horizon. This procedure will be repeated. So in this study, we consider a simplified shale gas production with a superstructure like this. Note that the candidate well paths are different in the number of states, the completion rate of the crew for fracturing, and also the pumping profile. The objective is to maximize the total revenue by simultaneously determining the fracture schedule and the pumping profiles. To formulate the integrated scheduling and control model in the outer loop, we first develop a reduced order model for hydraulic fracturing. In this study, the utilized high fidelity process model is developed by Prashant in our group, with which we are able to obtain the temporal evolution of the fracture lengths and fracture widths at different locations. Using the simulation data generated by this high fidelity model, the MOESP technique is utilized for model identification. The input variables are the pumping profile, including the flow rate and proppant concentration, and the output variables are the average fracture width, average fracture width at wellbore, and fracture length. Note that in practice, this average fracture width is unmeasurable and thus needs to be estimated through a Kalman filter. Also, the freshwater requirement can be directly calculated using the pumping profile, while the fracture geometry is used as the inputs to the CMG simulator to predict the corresponding shale gas production. Here are the list of detailed constraints used to formulate an integrated model. At the scheduling level, we have the assignment constraints, mass balance equations. The highlighted freshwater requirements and shale gas production are determined by the reduced order model as mentioned. Note that the availability of the freshwater is limited and the total shale gas production is restricted by the maximum and minimum demand, which are two of the underlying logics for the optimal solution. At the control level, we have the reduced order model as constraints. Note that since the hydraulic fracturing should be viewed as a fed batch process, the number of the reduced order models that have to be added is equal to the number of the candidate well paths. Also, the reduced order model is developed for each time period K, while the flow rate and proppant concentration are assumed to be the same within each pumping stage ST. The necessary operational constraints and other constraints required for the application purpose are also added. To link the scheduling control levels, the following equations are also specified. As mentioned before, the freshwater and proppant requirements are determined by the pumping profile, and the shale gas production is the function of the resulting fracture geometry. Here is the objective function. Note that in this study, we further consider planning decisions related to the freshwater impoundment, including the construction, the capacity, and the usage, all of which are used to formulate this impoundment cost. The resulting problem is a MINLP problem, and thus the linear and approximation techniques are considered here. One bilinear term in the model is the product of two continuous variables. In the case where the bounds are known, the product is replaced using a single continuous variable m, and it can be relaxed using the under and over estimators. In the case where the bounds are not known, we discretize one variable and disaggregate another one for approximation. Another type is the product of one binary variable and one continuous variable. Here, the big M reformulation is mainly used. With the three techniques, the original MINLP problem can be relaxed to an MLP problem. By solving it, we can obtain the optimal fracturing schedule. Then we fix the schedule in the original MINLP problem to get a smaller one, with which we are able to get the other decisions, including the pumping profiles, within a relatively short time. For the online control system, to reject the planned model mismatch unknown disturbances, we augmented the state system state with an additional integrating disturbance vector D, note that the BD and CD matrices should be chosen carefully to satisfy this rank constraints. This so-called augmented reduced order model is used in the optimal control problem instead of our original one. Besides, the Kalman filter is used as a current observer to estimate both the system states and the disturbances utilizing the available measurements. Here's the detailed formulation of the optimal control problem. The objective is to track the references, and thus the deviation should be minimized. The initial states are estimated using a Kalman filter unknown. With the augmented reduced order model and operational constraints, the optimal inputs can be computed online. Note that in each iteration, the optimal control problem is solved and to determine the complete input profile. However, only the first input is implemented to the process. Then the state is estimated again, and the calculations are repeated based on the new current state and the shrink time horizon. So the last section is about the obtained results. To show the performance of the developed reduced order model, 3 different pumping profiles are used for validation. It can be observed that the reduced order model has a reasonable prediction capability with a minor planned model mismatch. So here are the CMG maps generated based on multiple simulations. The left figure represents the cumulative share gas production as a function of fracture length and average fracture width. And the right one represents the share gas production ratio over time. Utilizing them together, the share gas production rate can be predicted. By solving the integrated model offline, the optimal fracturing schedule and pumping profiles are obtained simultaneously. It can be observed that for different well paths, the freshwater and proppant requirements, as well as the resulting cumulative share gas production, are completely different. It's worth it to know that well path 2, 3, and 6, which are to be fractured in the latter half of the year, are all designed to consume much more materials for much higher production amount compared to the first 3 well paths, which will be explained later. Also, the detailed pumping profiles show that for the first 3 well paths, the flow rates are actually designed to be always at lower bounds to reduce the freshwater requirement. The corresponding freshwater acquisition shows that all the available freshwater is utilized for well pad development, and the freshwater impoundment is necessary to achieve this, especially for well pad 3 and 6 represented by orange and purple. So based on the detailed share gas production, it can be observed that the production from the first, the second, and third well pads is mainly restricted by the maximum share gas demand represented by the red dashed line, while the one from the last 3 well pads is not. Besides actual share gas production, the actual share gas output is mainly dependent on the underground reservoir capacity and also the share gas selling price. As for the online control system, we compare the tracking performance from the nominal MPC system and offset-free MPC system. With the offset-free MPC, the tracking performance can be enhanced, and thus the fracture geometry gets closer to the desired value. However, for some well paths like the well pad 1 here, the offset cannot be completely removed. In this sense, we further test the results by relaxing the input constraints, considering that the flow rate designed for well pad 1 is always at the lower bound. Since the result is significantly improved, we think the reason is that the reference trajectory determined by the integrated model is not achievable due to the used reduced model. And another reason could be that the hydraulic fracturing process is a fat batch process and thus has no steady state. So it would be challenging for offset-free MPC to fully remove the offset. This actually remains the room place for further improvement. At last, the results obtained from directly applying the offline pumping profile and from the proposed framework are compared. It can be observed that due to the reoptimization procedure, the large economic loss that would happen without online implementation strategy can be avoided. So in conclusion, we can observe that overall economic performance of the share gas production system can be improved by using the integrated model. The tracking performance can be enhanced by using the offset-free MPC, and the large economic loss can be avoided by using the online integration strategy. In the future, we'll investigate better reduced order model techniques to generate more reliable reference trajectories. Also, we will apply this framework to large-scale cases and further consider spatial temporal variation in well characteristics and water management. Thank you. I want to conclude and happy to take any questions.